Presenting our project titled Housing Affordability Analysis Using Machine Learning and Neural Networks. This is a part of our class EAI 610, Applications of Artificial Intelligence. I want to now talk about why we chose housing affordability as the main problem for our project. Housing affordability is a major issue, economic and social issue, especially in urban and rapidly growing regions. Access to affordable housing affects financial stability, mobility, and overall quality of life. Because of this, housing data is frequently used not just by businesses, but also by governments and policymakers. One of the key reasons housing affordability is such a good use case for machine learning is that housing prices are driven by complex nonlinear factors. Prices is not determined by a single variable. Instead, it's influenced by combination of variables such as location, property type, tenure, and market conditions. These relations are rarely linear and often interact with each other in subtle ways. Another aspect is the presence of strong regional and categorical effects. For example, the same type of property can have drastically different prices depending on the country or region. This kind of structured categorical information is something traditional models often struggle with. That leads to the core challenges highlighted on on the slide, such as traditional models struggle with high dimensional categorical data, nonlinear feature interactions, regional heterogeneity across locations. These limitations make housing data a strong candidate for machine learning and neural networks, which are specifically designed to handle complexity, interactions, and scale. So the motivation for this project is not just predicting prices, but also understanding how different AI models have behaved when faced with a realistic, messy, real-world problem like housing affordability. So, what is the objective of our project? Now that we've talked about the motivation, the we can highlight on what our project hopes to accomplish. The first objective was to build a reproducible AI pipeline. That means every step from data processing to model training and evaluation is structured, repeatable, and consistent. This is important because in world AI systems, results needed to be reproducible, not just impressive ones. The second objective was to compare multiple machine learning and neural network paradigms on the exact same dataset. This, instead of committing to a single model early on, we intentionally evaluated linear models such as tree-based models, boosting frameworks, neural networks, and ensemble strategies. This enables us to observe how different model families behave when faced with this particular housing data. The third objective of our project was to evaluate trade-offs, not just accuracy. In practice, the best model is rarely the one with the lowest rare error alone. We explicitly considered trade-offs between predictive accuracy, interpretability, and computational costs. Some models are easy to explain, but limited in performance, while others are powerful, but harder to interpret or more expensive to train. Lastly, the fourth objective for the project is to demonstrate real-world decision relevance. Rather than treating this as purely academic exercise, we frame the outputs in ways that could support real decisions such as affordability, risk classification, model explainability, and robustness through ensemble learning. So this particular slide shows the high-level structure of the entire project. I want to talk through this at a conceptual level because everything we present later fits into this workflow. We start with data cleaning and pre-processing, which ensures the transaction data is valid and usable. This includes handling missing values, formatting dates, and preparing categorical fields. Without this step, model comparisons wouldn't be reliable. Next is the EDA, or the exploratory data analysis. This steps helps us understand price cat distributions, outliners, geographical variation, and temporal trends. The insights from EDA directly influence model choices later on. From there on, we move into feature engineering, where we select a consistent set of categorical features and encode them in a way that works across all models. This consistency is important for fair comparison. Once data is prepared, we begin modeling in stages. We start with baseline linear models to establish a reference point. Then we introduce tree-based model and boosting models, which are better suited for nonlinear relationships. After that, we explore neural networks as a more expressive modeling approach. Beyond pure regression, we then shift perspective by introducing affordability classification, converting prices into risk categories. This supports more practical decision-oriented use cases. Finally, we evaluate models using a champion challenger framework, construct ensemble um, models for robustness, applied model explainability using SHAP, and outline a time series extension for future forecasting. So basically, we can infer that the project is not a single model, but a structured end-to-end AI system. In the next slide, we're basically talking about the business side of it. Um, how the data used in this project, because of all the modeling, results dependent on the structure and quality of the data set. So the data set consists of UK property transaction records, and it represents a single year snapshot of housing sales. Each row in the dataset corresponds to one individual property transaction, which makes the data very clean and well-defined for supervised learning tasks. The primary target variable throughout the project is transaction price, which we use for regression. Alongside that, we include a small, meaningful set of categorical features, such as property type, new build status, tenure, and county, which captures geographical location. These features were chosen intentionally rather than engineering a large number of derived variables. We focused on attributes that are commonly available in real life housing datasets that have clear interpretability, and in particular, locations and property characteristics are also known to have a strong influence in price. In terms of pre-processing, we followed a minimal cleaning strategy. This included removing invalid price values and ensuring consistent formatting, but we also avoided heavy transformations. The goal was to preserve real-world data and variability rather than forcing the data into an artificially clean form. Uh, so for the next slide, we're looking at the EDA, or the exploratory data analysis. One of the first things we observed was a strong right-skewed price distribution chart, um, which I'm going to show in the next slide. Most properties fall within a relatively moderate price range, but there's a very long trail of expensive properties. This immediately tells us that the mean price alone is not representative, and that models assume normally distributed errors may struggle. We also observe extreme outliers. These are not necessary errors, but legitimate high-value transactions. Instead of removing them aggressively, we chose to keep them because they reflect real market behavior and test how robust different models are. Another important finding was monthly price variation. Even within a single year, median prices fluctuate from month to month, suggesting a seasonal or temporal effect in the housing market. This observation later motivated the idea of a time series extension. And finally, the most important one, we saw large regional price disparities. So the same property characteristics can correspond to vastly different prices, uh, to depending on the location. So this reinforced the importance of geographic features and suggested that simple linear relationships would not be sufficient. So this slide shows a visualization of the distribution of property prices in the dataset, including outliners. What immediately stands out is the strong right skew. Most property prices are clustered close to the lower end of the scale, while a relatively small number of properties have extremely high values. These high value transactions stretch far from the upper tail of the distribution. You can also see that these outliners are not minor deviations. Some properties are priced order of magnitude higher than the majority of the data set. Importantly, these are not data errors. They represent legitimate high-value properties in the housing market. From a model perspective, this has several implications. Firstly, it means that models assume normally distributed errors or symmetric price of behavior are likely to perform poorly. Second, simply removing these outliners would artificially simplify the problem and reduce realism, so we intentionally choose to keep them. This distribution also explains why RMSE values remain relatively high across the different models. A small number of very expensive properties can have a large influence on error metrics, even if predictions are reasonable for most homes. So now we go on the next slide for feature engineering. Our feature design the philosophy was to keep things very minimal and consistent across all the different models. Instead of enjoying dozens of derived features, we wanted to focus on how different algorithms behave when given the same core information. This also helps avoid feature leakage where models accidentally learn from information that wouldn't realistically be available in the predicted amount of time. Another key goal was to focus on algorithm behavior, not tactics. Um, if a model performs better, we want that improvement to come from model's ability to capture patterns and not just overly engineered inputs. The features we ultimately used are categorical and highly interpretable. Property type, new build flags, tenure, county. These are all features which are commonly available in real housing data sets and are known to have a meaningful relationship with the price of the housing. Because of all of these variables, which are categorical, we applied one hot encoding across the board. This encoding ensures compatibility with linear, tree-based, and neural network models and keeps the space consistent throughout the pipeline. Um, While this encoding strategy yields a high-dimensional feature matrix, it enables a fair apple-to-apples comparison across different model families. Any performance differences we see later can be attributed to the models themselves and not to differences in input representation. So, as you can see in this slide, for the price density and distribution shape, what's important here is not what just the price is skewed, but how extreme that skewness is. The median property price is around 28,280,000, which represents a fairly typical transaction. However, the upper quartile already jumps to roughly 43,000 euros and beyond that price. This rise very rapidly. You can see that the upper fence is around 80 million, 5,000, yet we still observe a large number of properties far above that average. Some prices extend into the hundreds of millions, with the maximum close to 480 million. These are extreme but very legitimate values that create very long trail in the distribution. From a density perspective, most of the probability mass is tightly concentrated near the lower end, while a small number of observations in dominance are in the upper range. This means that even a small number of predictions error on high value properties can have heavily influence metrics like RMSE. This distribution, however, has direct impacts for modeling. Linear models tend to struggle with this kind of skewness, while tree-based models, they can ensemble models are more robust to it. It also reinforces the idea that we avoided aggressive outliner removal. Removing these values would make the problem much easier, but less realistic. So we try to avoid that particular thing. Um, for this particular slide, it looks at the property prices over time plotted against the transaction date. At first, this visualization may look relatively very sparse, and that actually is an important observation by itself because the data set represents a single year snapshot. We do not see long-term trends like multi-year appreciation or just market trends. However, even within this limited window, we can still observe a short-term variation in transaction prices. What this plot, however, highlights is that property prices are not static, even over short period of time. Transactions occurring close together in time can still differ significantly in price, reflecting factors such as demand fluctuations, property mix, and regional timing effects. From a modeling perspective, this tells us two things. Two, firstly, purely static models that ignore time may miss meaningful temporal signals, even within a single year. Second, it motivates treating time as a first-class dimension when sufficient dataset is available. This observation is what later leads us to outlining a time series extension where prices are aggregated at the monthly level and modeled using sequence-based approaches like LSTMs. While we don't fully deploy that here due to data limitations, this slide shows why temporal modeling is a natural next step. So the next slide, this slide shows the monthly median property price trends across different years, from across different months. So this shows from March until November. Instead of plotting every individual transaction, we aggregate prices at the monthly level and we use median later than the median. Mean. This is important choice because the median is much more robust to extreme outliers, which we know are present in the housing dataset. What we observe here is a clear upward trend from the early months of the year into late summer and early fall. This pattern suggests that even within a single year, there are seasonal or cyclical dynamics in the housing market. These could be driven by buyer demand, interest rate changes, or seasonal moving patterns. From a modeling perspective, this is significant for two reasons. First, it shows that time is not just a choice, but also a meaningful structure in the data. Second, it explains why purely static models may miss important information if time is ignored. For the seasonal housing price patterns, this visualization, it's sort of it's unusual and it's different from the previous line charts. This particular model shows us the heat map, which is designed to highlight seasonality, how prices vary across different months within the year. The color intensity represents the median prices levels, with warmer colors indicating higher prices. What we observe is a clear seasonal pattern change. Um, Prices trend to be lower in the early months of the year, gradually increase it through spring and summer, and peak towards late summer or early fall. Towards the end of the prices begin to stabilize or slightly decline. This visualization reinforces an important idea. Housing prices are not only influenced by property characteristics and location, but also by the timing of the year. Seasonal demand, moving cycles, and a broader market behavior all contribute to these patterns. This particular chart shows price distribution across different counties. What's immediately clear is that location introduces substantially variation in housing prices, even when we look at only a few counties, we see that the typical price level and the spread of price differed significantly from one year to another. For example, in some years, most transactions are tightly clustered across lower price ranges, while in other years, prices are both higher on average and more sparse. Importantly, this variation is not noise, it reflects real differences in regional demand, economic conditions, and housing. So, this particular slide shows the top counties ranked by median property price, which gives a clear, more aggregated view of how location influences housing affordability. Instead of looking at individual transactions, we summarize prices using the median, which reduces the influence of extreme outliers and allows for a fair comparison between regions. What stands out immediately to us is the larger spread between counties. Counties like Greater London, Surrey, and Buckinghamshire have median prices that are significantly higher than the other regions. Even within this top group, their differences are substantial, where we're not looking at smaller variations, but gaps of tens or even thousands or hundreds of pounds. So the first model is the baseline model that we are using, which represents the simplest modeling approaches in pipeline. The purpose of these baselines model is threefold. First, they establish a transparent reference point for all advanced models. Second, it allows to quantify how much improvement we get from nonlinear approaches from later on. And third, we prioritize interpretability and computational efficiency, which are often desirable in real-world systems. All baseline models use the same feature setup. We, one, hot encode categorical variables such as property type, new build, flag, tenure, and county. This results in a high-dimensional but sparse design matrix with 123 different variables. Such Using the same input in representation ensures a fair comparison across the models. On the right side of the slide, we can see the performance for linear, ridge, lasso, and elastic net, and they have the RMSE and R2 score alongside it. This tells us something very important when you look at it. Regularization techniques like ridge and lasso improve numerical stability, but they do not meaningfully improve predictable outcomes. In other words, the issue is not overfitting, it's the linear assumption itself. Housing prices are driven by complex non-linear interactions between location, property characteristics, and market dynamics. So, linear models attempt to explain everything within a single global relationship, which is simply not expressive enough for this problem. So we use a second model, which is tree-based and boosting regression. The motivation for using tree-based model is straightforward. These models are specifically designed to capture nonlinear relationships that our linear models miss. They also naturally model feature interactions such as how the impact of property type can change depending on location. Finally, they are known to perform well on categorical tabular data sets, which makes them a strong fit for our housing dataset. On the right side, you can again see the model, RMSE, and R2 scores for all of the different models that we have used. The first important observation is that all tree-based models outperform the linear baselines. We see a clear reduction in our RMSE and our increase in R square across the board. This confirms that what we suspected from the exploratory dataset is housing prices are driven by non-linear dynamics that linear models cannot capture. Among these models, boosting-based methods is consistently perform better than single decision trees or even random forests. In particular, light GBM achieves the lowest RMSE and the highest R square, making it the strongest individual model set at this stage. It's also important noting that the performance differences between the top model are relatively small. This tells us that we are approaching a performance ceiling given the available features, rather than seeing dramatic gains from a single algorithm. So the key takeaway for this particular model is that tree-based models and boosting models offer a meaningful improvement over linear models by capturing nonlinear price dynamics, making them strong candidates for real-world housing data sets. So for the second model set, we're using um, this is the model comparison. What's important to notice here is that the bars are close together, um, and they're consistently ordered. All three base models are boosting models improved over the linear baselines we saw earlier, confirming that nonlinear modeling is necessary for this problem. So, in the third level, we used affordability risk classification. Instead of asking what is the exact price of the property, we ask a practical question. What is the affordability risk level of this property? To do this, we can prices into three affordable categories: low, high, and medium. These labels are derived using price quantities where the lowest third of prices is labeled low, the middle, and then the highest. This ensures that class act balance as shown in the distribution on the right side of the slide. This transformation is important for several reasons. First, classification outlines are often more actionable than raw prices. Policymakers, planners, and analysts frequently think in terms of risk tiers rather than exact numerical values. Second, this approach supports policy and planning decisions, such as identifying regions within high affordability pressure or targeting the interventions towards high risk areas. Third, it demonstrates flexible problem framing, which is a key skill in applied AI. In level 4, we introduce neural network modeling. The model here we use here is multi-layer perceptor, or MLP, a dense feed-forward neural network. We intentionally kept the architecture moderate because the goal was benchmarking, not aggressive hyperparameter optimization. On the right side of the slide, you can see the values, the model's RMSE score in R2. Ha. This shows that the model is nonlinear and it is essential for this problem. However, when we compare the neural network to the strongest tree-based models, we see that it does not outperform boosting methods. So this slide directly compares classical ML to neural network, using RMSE as the evaluation metric where lower values indicate better performance. On the left side, we can see linear-based models, linear regression, and ridge regression. They both have RMSE values around 2.099 million. These models establish a lower model of performance and confirm that linear assumptions are insufficient for this task. Moving to the center of the chart, we see the tree-based model and boosting models. Random forest, gradient boosting, and KG boost all reduce error compared to linear models. This with RMSE values clustering around 2.09 million. This confirms that nonlinear models significantly improve predictive modeling. The best performing classical model here is the light GBM with an RMSE score of 2.089 million, making it the strongest out of all the different models. On the far right, we see the MLP model. The neural network achieves an RMSE score of 2.090 million, which places it very close to the top performing model of Light GBM. This comparison highlights an important insight. While neural networks are highly expressive, they do not automatically outperform classical machine learning models in unstructured tabular data. In this case, boosting based models achieved slightly better score with less tuning, lower computational cost, and greater interpretability. This is our last level, which is level 5. We focus on model explainability, which is a critical requirement for deploying high-performing models. Models in real-world housing analytics. As we've seen in early slide, the best performing model so far has been Light GBM, which behaves almost like a black box scenario kind of thing. While they achieve strong predictive performance, they do not provide intuitive explanations for why a particular model prediction was made. This is a serious concern in the the domain. Housing analytics directly impacts policy decisions, urban planning, and equity considerations, so model outputs must be transparent, interpretable, and defensive. To address this, we apply SHAP, or Shapely Additive Explanations, to our champion model, which in this case is light GBM, with an RMSE of approximately 2.089 million and an R square of 0.00345. SHAP provides two levels of insight. First, it offers global explanations showing which features are most influential across all predictions. Second, it provides local explanations, allowing us to understand why a specific prediction was high or low for an individual property. Importantly, SHAP uses a small game theoretic framework, ensuring consistent and fair um, prediction. So now we're going to talk about the champion challenger framework. After evaluating all the different models, the next step is to decide how a model would actually be selected and maintained in practice. This is the champion challenger framework. The selection criteria here are intentionally simple and objective. The champion model is defined as the model with the lowest RMSE score. In our case, this is the light GBM with an RMSE score of 2.089 million and R square of 0.0345, making it the best performing model out of all of them. Rather than stopping here, we also identified challenger models that perform slightly worse than the champion, but are still within a reasonable margin. In this project, the top challenger is the random forest, XG, and MLP. All these models achieve RMSE values very close to the champion, indicating comparable predictive strength. This framework is important for several reasons. First, it avoids over-reliance on a single model. It supports controlled upgrades, and it mirrors real ML governance. For the ensemble learning, the motivation for using an ensemble is very straightforward. Instead of relying on a single model, we combine the strengths of multiple different models. This helps in um, reducing variance, smooth out model-specific errors, and improve overall robustness across the different data distribution changes. Second is reduces variance, and the third is it improves robustness. So this is a chart for champion versus ensemble model comparison. On the left side, we can see the champion model, which is light GBM. It achieves an RMSE score of 2.09 million, versus on the right side, we can see ensemble model, which has an RMSE score of 2.0898 million, which is slightly higher than the champion, but very close to the magnitude. This comparison highlights an important point. From a very purely metric-driven perspective, the champion model is marginally better. However, the differences between the two is very relatively small in a Hassen kind of perspective. So this is a SHAP model that we had initially talked about. Rather than focusing on the aggregate metrics like RMSE, SHAP allows us to answer important questions. Why did the model make the specific particular prediction? Let me very briefly explain how to read this visualization. The value in the center represents the baseline prediction, which is essentially the average predicted property price across the dataset. Each feature then pushes the prediction higher or lower to that baseline. Features shown in red push the predicted price upward, while features shown in the blue push it downward. The length of each bar indicates the length of that feature contribution. Now for the ensemble learning, the motivation for this one is housing markets evolve over time, static models ignore and temporal dynamics, and the approach is monthly median prices aggregation. LSTM outlined this for seasonality and long-term trends, and the status of this particular model was not fully developed and demonstrate pipeline extensibility. What worked for our project versus what did not work for us is what worked well is the boosting models such as Light GBM and XGBoost. Ensemble strategies work for us, SHAP experimentally work for us, and then Champion Challenger work for us. However, our challenges where neural networks require heavy tuning, time series modeling limited by data scope, linear models insufficient for complexity. So what are the takeaways from our project? So no single best model across all the objectives, trade-offs, accuracy, and temporally robustness matter more than RMSE alone. Explainability is essential for housing and policy-related analytics. And lastly, ensembles improve robustness under data noise and uncertainty. Thank you so much.